Yes, your questions.
In Young's double slit experiment, the observers see that electrons make interference. After that, some people go to this screen to find how they make this interference. But when the observer is on this place, on the screen, the electrons makes a Gaussian distribution. Is that true?
It's not necessarily Gaussian. It's not Gaussian. It's more like sine squared by sine squared x by x squared. It's not Gaussian. It looks like Gaussian, but that's not the. You see, it is this function.
Is that same function?
It should be something like sine squared x over x squared.
But it's interference.
Yes. This is the final result. But for us, the important thing is not actually the shape, but the fact that there is interference, even for the electrons. And it wasn't only in the double slit experiment. In fact, the first observation was made in a crystal. So you have the crystal, and using X-ray diffraction, you know the crystal spacing. So this spacing is known. So if you send a beam of electrons, well, in the actual experiment, what they had done was they sent the beam, this was the crystal, they sent the beam in this direction, the electron beam. And the electron colliding with the material inside the crystal, it just, some of them scattered, some of them just went through. And if you put a detector somewhere over here, then you can measure the amount of electrons that move in the direction of your detector. So how many of them scatters in that direction? And the final result was, it's plotted something like this. More or less like this. So how to read this graph, or let me start from here. How to read this graph is, let's say, you given an angle, the length of this vector is kind of the intensity. So if you, well, depending on your angle, you look at your angle, various angles, you see that at a given angle, there's a peak. Well, this is not a nicer graph. It has a shape more or less like this. So what you do is you just put your detector, you move your detector around. At some particular angle, there's an enhancement. You wouldn't expect this in the classical physics. So what you would expect most probably would be, most of them would go through, some of them will scatter, but those who scatter a very large angle should get smaller and smaller. But what we see actually is that at a given angle, there's a peak. Just like this one, more or less. You see, this is a linear screen, but if you just imagine converting it to angles, most of it goes straight. But if you look at a particular angle along this direction, you see an enhancement. An enhancement and a suppression, enhancement and suppression. This graph is just like that. You see an enhancement, some suppression, and then there's no more interference pattern. Interference pattern is lost. But you have a suppression. This was the first observation. And then you can look at what is the wavelength creating this suppression. And you can do an X-ray experiment. And the X-ray experiment just shows us that at this angle, exactly at the same angle, by the way, even in the X-ray experiment, you have a suppression. And the wavelength is something like 0. In the experiment, what was used were electrons with an energy of 54 electron volts, which, according to de Broglie, corresponds to a wavelength of 0.14 nanometers. And in the X-ray scattering experiment, it's also known that for this wavelength, at the same angle, you get a suppression. So this is also another verification another enhancement, sorry. So this is, in a sense, another verification that the de Broglie formula is correct. So there does correspond a wave to the electron, and whose wavelength is predicted, at least in these energies, the de Broglie expression is the correct expression for the wavelength. So if you remember at the beginning of this discussion, we said that a characteristic phenomena of waves is interference. So here, electrons showing interference pattern. Other questions? And if you remember, on Monday we were discussing about wave packets. So if you know that there is an electron, let's say at least classically, if you know that there is an electron over here, what it actually means is that, just think of your measuring equipment. Your measuring equipment has an uncertainty. You cannot determine the position of an electron, even classically, very precisely. So what you know is your electron is with a 99% probability somewhere here. Now, what this wave, the corresponding wave, should have something of this form. So the probability of observing the electron, your particle here is 0. There is some finite probability in this region. Let's say it has such a shape. We don't really know the shape for the time being, but let's just make up a shape. And then nothing over here. This is my wave, the wave amplitude. And we said that the probability density is proportional to the absolute square of this one. And then we said, okay, if it is a wave, we can write every wave in terms of harmonics. Where omega was E over h bar, and k is equal to p over h bar. So this should be our wave describing my particle. Any questions here? Because just saying that I should describe my particles as a wave will have important consequences. One of that will be the uncertainty principle. This is just a result of the fact that now we know that we should describe particles as waves. You see, when we started with a harmonic wave, this wave has this shape. If you take its square, this is psi of x. If you take its square, well, this is what you will get. Well, essentially the probability goes everywhere. So if this cosine wave was the wave describing my electron somewhere over here, it would just tell me that my electron is kind of everywhere. The probability of having that electron is everywhere. I cannot just say that my electron is over here. It just doesn't make sense. To be able to describe an electron whose position I know is somewhere over here, maybe not at this point, but somewhere over here, what I need to do is I need to create a wave that has something of this shape. At least in this case, I know that my electron is somewhere within this range. There is no probability of observing this particle, neither here nor here. But now I have to create such a wave. Well, how do I create such a wave? I just add many harmonic waves, not just that one, but I add many of them. Now let's just see how it works. This capital N is essentially the number of waves I have. So here, if you look at the top, it's just the cosine of n pi x. Well, let me just put 0. No wave. K is 0, so my electron it doesn't have any momentum. It can be everywhere. It has 0 momentum. Well, let me just add 2 terms. The constant term, if you look, my function is at the top. This is just 1 plus the cosine. It's still, well, I just plotted from -1 to 1, but if you can just imagine it to extend, just to oscillate up and down up to infinity. Well, let me add one more. Well, you see already, now here I have the constant term plus 2 cosines. Already the probability of observing this particle in this region below x is equal to, let's say, -0.3 and above x is equal to 0.3 is much smaller than the probability of observing it between these two limits. So if this is my wave, I now can say that my particle is most probably around x is equal to 0.
In such a function, what is the significance of negative probability?
This is not the probability, this is my wave function. The probability will be the square of this one. When I take the square, keep in mind that these will get even smaller. As you wish. Happy? This is the probability. Now I have just 3 terms, the constant plus 1 cosine plus the second cosine. Well, you see the probability that my particle is in this range is large. Out of this range, the probability is very small, almost non-existent. So let me add one more wave. This is what I get. You see, it now becomes narrower, this peak. Other peaks become smaller.
Buradaki dalgalar tek dimension'daki
Yes.
üzerindeki. O zaman iki tane dalga hour2 phase shift'i olsa ve aynı peak, yani aynı intensity enerjiye sahip olsa bir çizgi elde ediyoruz değil mi? Yani böyle olduğunu varsayalım.
Well, for the time being, what I'm doing is I'm just trying to create one wave for one particle. That's what I'm trying to create.
Ama bir dalga hiçbir zaman yeterli olmuyor.
That is the idea. One harmonic wave is not enough to describe a particle that we know is somewhere over here. Because if we have one harmonic wave, my particle can be anywhere, not necessarily in some small volume. You see, let me just increase this number to 100. This is what I get. To be able to have a wave describing a particle that I know is at this point, I'm definitely sure that it's at this point, I have to add many waves. That is the lesson that I would like you to learn in this demo. Are you convinced? Why aren't you convinced? Yes.
Burada konumunu %100 olarak bilmemiz hızını ya da momentumunu da sıfıra indirgemiyor mu?
Yeah, we don't yet, I'm not yet discussing any other thing yet. I'm just looking at the position. What I'm saying is, if I want to create a wave describing a particle whose position I know almost for sure, whose position I am sure that it's in a very small region. To create a wave describing such a particle, I have to add many cosines. Yes.
As we go on, they will never be zero. So, is this just a fault in the modeling, or is it the reality?
Well, you see, in reality, you are not adding cosines. So it's not a problem in reality. But at least if I'm trying to model it mathematically, I have to add many cosines to it. If I would like to obtain this one as a sum of cosines, I don't have to obtain it as a sum of cosines. But if I add it as a sum of cosines, then, as you said, to get a really peak, which is zero everywhere else, I have to add infinitely many of them. But since in reality that's not what I'm doing, I'm not adding cosines. That's not a problem for reality.
The better formulation,
Better, what do you mean?
better mathematical modeling.
I mean, this is good enough. You see, since this is just a modeling, I can add infinitely many of them. There's no problem with adding infinitely many of them. So I can get exactly zeros over there. Not on the computer, but I can get exactly zeros.
Bir particle için o zaman karakteristik tek bir tane dalga fonksiyonu var değil mi?
Exactly. We cannot say that. You see, if we know that there is a particle in a finite region, let's say, then one thing that we are sure is that we cannot say that there is a single harmonic wave. The wave describing this particle should be the sum of many harmonic waves.
Hocam, burada yaptığımız şey tam olarak bir tane wave'i bir sürü küçük wave'in süperpozisyonu olarak yaptık.
Yes, exactly.
O zaman aslında yaptığımız şey aynı wave'i sadece giderek incrementine ama giderek küçültmek. O yüzden mi biz bu kadar exact bir değer alıyoruz? Yani aynı wave'in başka küçük şeylerin süperpozisyon olarak haline yazdığımızda aynı değeri direkt yazmamız arasındaki fark neden bu kadar diye düşünüyorum.
We will come in a moment. Why this will be important. Now, any questions on this demo? Now we will discuss the implications of this demo. Some of you have already figured out. You see, one thing is we cannot just say that this is a simple wave. This is not a single harmonic wave. It's just the sum of many harmonic waves. Now let's combine this with this knowledge. That K which is 2 pi over lambda is P over H bar. Now, what did I do over there? You see, look at this way. I just ignore the time dependence. It's just cosine n pi times x. So the wave that I'm describing over here, let's say test, is 1 over square root of n, sum n from 0 to infinity, cosine, let's say kn of x, where kn is just n times pi. Or we can say that Pn is h bar times n times pi. Now, saying that this is not just a single harmonic wave is actually the saying that this corresponds to not a single momentum, but many momenta. You see, a particle that has a definite momentum and a definite energy has a definite wave vector. If P, you know P definitely, then you know what the K is. Knowing K means it's just a single harmonic wave. But the single harmonic wave just extends to infinity. So you practically have no idea where the particle is because the wave extends to infinity. Now, to get over that, what you do is you just add many harmonic waves. But if you add many harmonic waves, then you can create this wave function that is localized in a given in a finite region. But that means you are adding many values of momenta, many different values of momentum. So if you measure the momentum of the particle, you can basically determine any one of them. So it tells us that if you try to localize your wave function by adding many harmonic waves corresponding to different momenta, then you don't know the momentum of the particle. You know the position now, but you don't know the momentum of the particle.
Harmonik wave yerine başka bir wave kullanabilir miyim? Yani sonuçta bunlar kompleks exploration'ın şeyi ya hocam, real ya da imaginary partları ya. O yüzden kompleks cebiре çevirsek başka bir harmonik wave yerine başka bir wave kullanabilir miyim?
Okay, let me make a couple of changes. You see here, I just looked at one particular test wave, let's say. Not all waves have this form, you see. I can create waves by summing different cosines with different coefficients. Here all the cosines have exactly the same coefficient. I don't have to have all of them of the same coefficient. So that will tell me a wave, its value at the point x. Now this is a sum. It essentially creates a periodic wave. So that's why I was restricting x from -1 to 1. But in reality, the wave of a particle need not be periodic. So if it's not periodic, instead of Fourier sums, let's say, you have Fourier integrals. So an arbitrary wave you can write in this form. Well, it's just, instead of sines and cosines, if you like, I can just use the imaginary expression from -infinity to infinity. This contains both the sines and the cosines, well, everything. And psi need not be real anyway. Now, how do we interpret this? We say that psi of x squared is the probability density that the particle is at the point x. Now this other one, phi of k, we call it the probability density that the particle has wave vector or if you like, it's just nothing but the momentum, the wave vector k, or if you like, the momentum h bar k. And this demo over here is just choosing one k vector, that's just a single term in this sum, basically means that phi of k is non-zero only at a particular value of k, and it is 0 everywhere else. So this function phi of k is very narrow. If that is very narrow, then I know what the value of k is. Let me just draw some sketches. Now, this is phi of k. This is psi of x. Now, if phi of k has this shape, essentially I'm just looking at one k value, this value, then psi of x has this shape. My particle can be here, it can be here, it can be here, it can be here, it can be anywhere. If phi of k gets larger, let's say if this is our phi of k, then psi of x becomes something like this. Now the k value of this particle can have this value, it can have many values. But the x values, it can still have many x values. But the allowed x values are limited in range. I can choose psi of k or phi of k to have such a shape, or if you like, constant. That was the example that we had looked at. If phi of k is constant, then psi of k, psi of x just became this one. If you choose one of them to be narrow, like this, the other one becomes very broad. And there is no way to avoid it. So this is the essence of the uncertainty principle. You see, you can say that this is the uncertainty in k, and this is the uncertainty in x, meaning that if you measure the position of this particle, you most probably will measure some position within this range. If you measure the momentum of this exactly the same particle, or the wave vector of this particle, you will measure something in this range. You will not get a single value. You will get many values. And their product is always larger than or equal to 1/2. Well, P is just multiply both sides by h bar, and you get delta x times delta P is always larger than or equal to h bar over 2. This is the Heisenberg's uncertainty principle.
Bu ölçme sorunu bizim bir problemimiz değil de doğaya içkin bir özellik değil mi? Doğa kendisi böyle davranıyor değil mi?
Well, that is our interpretation. it's not just our equipment is not good enough. It's just no matter how much advanced we are, we will never be able to determine the x and p of a particle with a bigger precision than allowed by the Heisenberg's uncertainty principle. It just doesn't exist. This is just a direct consequence of the fact that particles are waves. Questions?
Hocam şey soracaktım. Hocam o zaman diyebilir miyiz ki bizim varlığımız olmadan herhangi bir dalganın oluşturduğu momentum olan? Yani orada biz varsak o zaman dalganın momentumu. Biz yoksak yok.
Without measuring it, the momentum of the particle, the concept of the momentum of a wave or a particle just doesn't exist, doesn't make sense. And if you measure the position, its momentum is again doesn't exist.
Yukarıdaki grafiklerde Fourier transformu sayı k ve fonksiyon k'ye bağlı bir grafik değil mi? Yani tam olarak hani population
Now let's also make a concrete definitions of these concepts. What do we exactly mean by delta k and delta x? But just from the graph. Now the average of x. Well, the average of any quantity, you just multiply it with the probability and sum them up. This is the average of x. The average of p, or let me still use the k, the average of k will again be just k multiply with its probability. This time it is phi of k, and then sum them up. Then you can look at x minus the average of x. Now, if you look at the average of this thing, so how much your x values change from the average, this is just 0. So what you look at is the square of this one. This is what we define as delta x squared. And similarly, k minus the average of k squared, and its average, this is what we call delta k squared. The product of these things is always larger than or equal to 1/2. Where? No, there's no squares over there. Yes? That's the definition. Take this square root. Well, let's do an example. Let's look at psi of x. This is equal to some number a e to the power minus, let's say x minus x0 squared over sigma squared. Let's assume that this is my wave function. This is a wave function that will look like this. It's maximum at the value x0 and just goes to 0. So let's start with what is a. Well, we can determine A. If you remember, psi of x squared is the probability density. The total probability should be 1. So just integrate this probability density over all space. So this should be 1. Well, this is equal to a squared. Now let me put a 2 over here also in the definition. From minus infinity to infinity, e to power minus x0 squared over sigma squared dx. This integral should be 1. Let me make a change of variables. Let me call y as x minus x0 over sigma. So dy is equal to dx over sigma. So 1 should be equal to a squared sigma from minus infinity to infinity e to power minus y squared dy.
Bence şurada da karesini alalım. 2 adım üstte e to the minus x square divided by sigma square square.
That's what I did.
Böyle. Tamam.
You see, over there I have a factor of 2. When I take it square, it just disappears. Do you remember what this integral is? What's the value? Over 2 or not over 2? It's just square root of pi. If you take it from 0 to infinity, it's over 2. If you have, instead of minus y squared, if you have minus alpha y squared, then it's square root of pi over alpha. Well, this already tells me that the absolute value of A should be equal to 1 over sigma square root of pi, all of this under the square root. So this is what the A should be. Well, we only know the absolute value. We don't know the sign. We don't know the phase. If it can be a complex number. Well, the convention is you most of the time ignore the phase. Sigma to the 1/2 pi to the power 1/4. So this is our A. Now let's try to find the average of x. Well, the average of x from minus infinity to infinity, x times psi of x squared dx, which is absolute value of a squared. You see, the sign of a or the phase of a is not important because almost everywhere it will be the absolute value squared that will enter. A squared times from minus infinity to infinity, x times e to power minus x0 squared over sigma squared dx. I will make exactly the same change of variables. So the average of x will be a squared sigma from minus infinity to infinity dy e to power minus y squared. Well, you see, this tells me that x is sigma y plus x0. So this is equal to x0 times a squared sigma from minus infinity to infinity dy e to power minus y squared plus a squared sigma squared integral from minus infinity to infinity dy y e to power minus y squared. What is this integral? The first line. Now you see, the first line is a squared sigma times that integral, which should be 1. A squared sigma times this integral. Well, that's how we define the A. A was chosen to make this combination equal to 1. So the average of x is x0 plus, what is this integral? No? Is the integrand even or odd? The integrand is odd. The integration region, is it even or odd? It's even. If you integrate an odd function over an even region, it just gives you 0. Basically, you are summing, let's say, y is equal to 5, and you are also summing y is equal to minus 5. This value just changes sign. So you are summing some number and minus that number, it will give you 0. So kind of, at least it makes sense. You see, if you look at our wave function, what does this tell me? If I would create many copies of the same particle, having this wave function, the probability of observing the position of that particle here will be proportional to this number. The probability of observing it here will be proportional to this number. The probability of observing here will be proportional to this number. So if I have millions of them, I will just measure just a few of them at these positions, this position or this position. I will measure thousands of them somewhere here or here, and millions of them somewhere here. If I just average my measurements, then the average position will be just x0. And that is what we obtained. Now let's see the uncertainty in x. You see, the delta x squared was defined as x minus the average of x squared, all of this average. This is how we defined it. Well, this is equal to x minus x0 squared average, which is equal to, the definition of average is from minus infinity to infinity dx x minus x0 squared e to the power minus x minus x0 squared over sigma squared. How do you take this integral? Let us, no, let me leave it this way. Do you know how to evaluate such integrals? Well, there are several tricks. Let me use one of them. This is from minus infinity to infinity dx x minus x0 squared e to the power minus alpha x minus x0 squared, with alpha is equal to 1 over sigma squared. Well, let me just consider this term. If I take the derivative with respect to alpha, what's the derivative? Y2. Keep in mind, I am taking the derivative with respect to alpha. Well, yeah, it will be the same exponent multiplied with minus x minus x0 squared. Well, almost exactly like this one, with an extra minus sign. So let me just multiply it by a minus sign also. But now, derivative with respect to alpha and integration with respect to x, they are independent things. I can just change their order. And that integral will be minus d over d alpha square root of pi over alpha. By the way, I forgot some a squared over here. Because everywhere I need to have a squared. A is independent of alpha. Well, just take the derivative. It will be, well, minus 1 half alpha to the power minus 3 halves square root of pi times a squared. So this minus signs, they just cancel. And keep in mind that this should be evaluated at alpha is equal to 1 over sigma squared. So this is equal to 1 over 2 times sigma cubed square root of pi a squared. Well, let's see what a was. This is equal to 1. So this tells me that the uncertainty in the position of the particle squared is 1 over 2 sigma squared, sigma square root of pi a squared. This is 1. So delta x squared is sigma squared over 2. Or delta x is equal to sigma over square root of 2. This is the uncertainty in the position of the particle. Now let's do the same thing for the momentum. You see, my wave function is this one. This is the wave function I used. A is this overall constant. And that constant we chose to fix the total probability to 1. It's the amplitude. No, this is still the amplitude. Now, the probability in K-space, we define it through this relation. So what is your phi of K? It's a similar integral, e to the power minus I kx. We are integrating this time psi of x dx, and you have to put some 2 pi somewhere. Well, we know what psi of x is, minus infinity to infinity, e to the power minus I kx, a, e to the power minus x0 squared over 2 sigma squared, dx over 2 pi. Do you know how to evaluate this integral? I'm not going to evaluate it. I wouldn't like to bore you. But, well, for this purpose, we have nice computer programs. So essentially, phi of k will be some constant b. It will depend on a, k0, k, and x0. Then you have e to power minus 1/2 k squared sigma squared. If you just multiply, this is k squared sigma squared. Then you have minus I k x0. This is our phi of k. Well, the probability is the absolute squared. So this is absolute value of b squared, e to power minus k squared sigma squared. This is the probability. Well, when you take the absolute value, this term is just not important. But now let's see, compare this with psi of x squared, which was e to power a squared, e to power minus x0 squared over sigma squared, 2 sigma squared. The average of x was just this number over here, x minus x0 squared. Here it's just k minus 0 squared. Let me just rewrite it like that. K minus 0 squared. So the average of k is 0. Here the average of x was x0. Now on the right-hand side, the average of x minus x0 squared, this was, let's just look at sigma squared over 2. Well, that is nothing but this factor dividing x minus x0 squared. Well, that factor, all of this, divided by 4 is this one. Well, the algebra, the mathematics over here, it will be identical. So the average of k squared, let me put k minus k0 squared. This will be, well, the factor dividing minus k squared is 1 over sigma squared. Let me divide by 4, just like over there. I mean, you can just redo the algebra and explicitly show that these are correct. So this told me that delta x was sigma over square root of 2. Well, this tells me that delta k is 1 over 2 sigma. So delta k, delta sigma is 1 over 2 sigma, sigma over square root of 2. Sigma is just cancel. Well, I have made a mistake somewhere. So you can just check the computation. One over 2. You see, in fact, this is a special wave function for which delta x times delta k is not larger than 1 over 2, but exactly equal to 1 over 2. It's the wave function that has the least uncertainty. This is the wave function. You see, if you look at the probabilities, both the probabilities have exactly the same form. They are not equal. They have the same form. Well, A and B, they just raise or lower the wave function. So you just fix them to fix the normalization. The average is more or less, you can think of the average of a quantity is its center of mass. So if you just double your particle, the center of mass doesn't change. Just like that, the average of X or the average of this quantity does not change. But kind of you have a point though. So that the A and B doesn't change the physics. If you use the physics and interpret the physics consistently.
O zaman dalganın wavelength'iyle ilgilenmiyor. Sadece maksimum ve minimum. Yani.
You see, in general, a wave doesn't have a wavelength. In general, only harmonic waves have a wavelength. Harmonic waves are the waves that you can be described by a single cosine or sine. Only those have a wavelength. Others do not. Okay, let's give a break, and then we can continue.